Hey everyone, in this video we're going to start Unit 6, which is all about using integrals in applications. Specifically in Section 1 we're going to be looking at accumulation of change. We're going to be using integrals to total up how much something changed. You may remember we did this a little bit back when we introduced the fundamental theorem of calculus back at the end of Unit 4. We're going to first bring back, I got a little review problem here for you to start. And then we'll start to introduce some more stuff as we go through the pages. So up first, I have a physics problem for you, a particle motion problem, which this is the one style of accumulation of change problem we did back in the fundamental theorem of calculus topic section. And so you'll see the graph on the right represents the velocity. Okay, so we have the velocity of an object moving at time t for 10 seconds. And what you'll see is I've given you the area underneath each of the boundaries of the shape here. So 32, 8, 16. And let's look at our questions. So if you want, you could just take a stab at this. You could pause the video, take a stab at it, fast forward till you get to the answers. If it's been a while, you can certainly just follow along with me. So let's see. Our first job is to figure out when the particle is moving to the right, to the left, and when it is stopped. These are all velocity ideas. So we're looking for where is the velocity positive, where is the velocity negative, where is it 0. So we'll say to the right, where velocity is greater than 0, which happens to be where time is between 0 and 4 seconds, and again from 8 to 10. Wherever the velocity is negative, then would be where it's moving to the left. Which would just be from 4 seconds to 8 seconds. And then it's stopped wherever the velocity is 0. So that would be at 4 and 8 specifically. Again, like we said, we've said this a few times by now, you can also use open intervals. You do not necessarily have to include the zeros there. I would still go ahead and include 10 because it's an endpoint that's positive. Just pick one way and stick with it. Brackets are fine as well. Okay, so then part B is where we'll start looking at some change. We have find the displacement for the given time interval. Then if s of 0 equals -5, that would be an initial condition, initial position or initial condition. What is the particle's final position? Okay, so remember, integrals accumulate change. So way back when, it wasn't that long ago, we said displacement, which is also final position, final position minus initial position, is the integral from A to B, the 2 times of the velocity graph. So displacement, which is final position minus initial position. So we would say final position, that would be at time 10, so the position at 10 minus the position at 0 would equal the displacement, the integral from 0 to 10 of the velocity graph. So actually, I guess I had 2 questions here. So we should probably take a second. We should just point out that that integral itself can be found by totaling up all of these. Make sure you consider the one below the axis negative, because that would be when it's got a negative velocity, so it would be displacing backwards. So let's see, 32 and 16 would be 48. Then minus 8 would give us a total of 40. So that's one of our answers. And then the other one is to find the final position. So the position at the 10th, what is it, second minute, something like that, second, would equal 40 plus the initial position, which we said was -5. We got that back here. So I think our final position then would be 35. And I'm checking for units here. Where's the line? We do not have units, so we can just leave it as is. Finally, find the total distance traveled by the particle. Remember, total distance, that is similar to displacement. The only difference is we need the integral of the absolute value of the velocity. So here, going from 0 to 10, I ran out of room, heck. Well, let's just write over it, shall we? Going from 0 to 10, this would be, well, sorry, absolute value, velocity. This would equal all of these individual areas added up, forgetting the minus on the bottom here. So we would just say that's plus 8 as well. 32 plus 8 plus 16. So let's see, 48 and 8 would give us 56. And again, if we had units, I would label them. I do not see units here, so I think we're good to leave it. So all's well and good here, especially because we did not have to actually find those areas, right? They were just given to us. In the next problem, it's very similar, but we're going to make you do a little more work. So this is a non-calculator question, but instead of a graph, instead of giving you the areas ahead of time, I'm giving you an equation which represents the velocity. And I did go ahead and give you units this time, so we'll pay attention to that as well. Our job is to use analytic methods, that means by hand, to find the total distance traveled. Okay, well, let's break it down into pieces. Total distance would be the integral over the whole time of the absolute value of the velocity function, which would be the integral of 0 to 6, absolute value, t squared minus 6t plus 8. Now you're probably looking at this and you're thinking, why is the spacing off here? I don't know. I just noticed that myself, and that was what I was thinking as I was starting this problem. No, you're probably looking at this and thinking to yourself, we've never even graphed an absolute value of anything that's higher order than linear, let alone integrate. Mr. Dune, are you crazy? Only a little, but that's for other reasons. Let's just start by using some pre-calc methods to sketch what the function would actually kind of look like. So the original function, not in the absolute value, just the quadratic here. Well, let's see. I know it's positive t squared, so it's got to open up, right? And we only have a couple options. If it's opening up, we've either got something that would have no intercepts, no t-intercepts, or it's going to have two. Oh, I suppose it could also have one perfect one like this. But whether it has one or none, well, that wouldn't influence our absolute value integral, would it? Because we just always have positive area. The only possibility that could actually force us to do something weird with the absolute value is if we had a quadratic that kind of cut the y-axis, the x-axis, the time axis, sorry. So let's make a sketch here real quick. It's a quadratic, so we'll be stepping back to some pre-calculus here, but I want you to ask yourself, where would its t-intercepts be? Where would its intercepts be? Because that is the only place where it can change from positive to negative. T-intercept where? I'm really good at making notes, you guys. So let's see. Time-old strategy. Set it equal to 0. Try and solve. Well, you could quadratic formula because it's a quadratic, right? But it's also a quadratic, so we should probably try and think about factoring. You can't always, but sometimes you can. Here, it looks like we can because nope, wait, hang on, I made a mistake here. I think it'd be double minus, wouldn't it? Yes. So -4, -2 make positive 8. -4 minus 2 makes -6. This checks out. Okay, so our t-intercepts are 2 and 4. And then I know the graph opens up, so I know it's going to do something like this, again, because it was positive t squared. So I know here's my 2, here's my 4. So here's what we're going to do, guys. We're going to split this up, this integral. We can keep the regular integral from 0 to 2 of the velocity function, because it's going to be giving us positive area there. Here's 0, so we're going to get positive area up until 2. Plus, then we would need to treat the upcoming negative area as positive. Well, since we've already we know this is going to come out negative, we can just do the regular integral from, 2 to 4 of the velocity function. And we're going to take whatever number that gives us out and put it in absolute value. That way it's forced to be positive instead of negative, like it's going to be over here. And then finally, to get the other positive area over here, we'll do one more integral, just regular, from 4 to 6. This looks worse than it is. You're looking at this and you're probably thinking to yourself, I got to do 3 integrals to really solve 1? No, you don't. Look, the inside is the same every time. We're integrating the same function, so I only have to do that once. Let's do that right here. Let's say our antiderivative, which let's just call it s of t. Let's give it a name because we're going to use it a whole bunch. Our antiderivative of the velocity function of regular v of t, not v of t in an absolute value, would be, let's see, power rule 3 times. So t cubed over 3 minus 6t squared over 2, which we could reduce 6 over 2 is just 3. And then plus 8t. Now, again, you could write this out a million times. You'd write it, you'd evaluate between 0 and 2. You'd evaluate it between 2 and 4, and you put an absolute value, 4 and 6. Or you could use the other notation. I don't do this very often. You'll see me only really use this in context problems, kind of like this one. But any integral, when evaluated, is the antiderivative at the upper limit minus the antiderivative evaluated at the lower limit, right? This was the other way we notated it back in Unit 4. We just, typically when you're evaluating numbers, it's easier to use the bar, but you can also use this notation as well. So there's our first integral, plus, now I need my absolute value, doing it with 2 and 4. So upper limit 4 minus lower limit 2, close the absolute value, plus one more time with 6 and 4. Antiderivative at 6 minus antiderivative at 4. And okay, still bad news, right? Because we've got to evaluate this function at 1, 2, 3, 4, 5, 6 places. Nope, here's another advantage to doing it this way. It's not going to save you a ton of work, but look, we reuse s of 2 twice. We use s of 4 twice. So, you know, s of 0, s of 6 each get used once. So I would then suggest, dang it, why did I highlight? Because it's always hard to erase highlighting here. You don't even have to work this right on the page. You might, or right there on the page, you might just give yourself a little space off the side. Say, okay, I'm going to evaluate s of 0, s of 2, s of 4, etc. And then we can just put the numbers in here where we need them. But at this point, we're just doing algebra and arithmetic to finish up. We've done the calculus. Now we just got to plug the values in. So let's see. If I plug 0 into our antiderivative function up there, I'll get 0 minus 0 plus 0. Hooray, 0 is our favorite number to work with, isn't it? If I plug in 2, let's see. It's going to be a whole bunch of thirds, but let's stick with it because it's a non-calculator question. Let's see. 2 cubed over 3 minus 3 times 2 squared plus 8 times 2. So what do we got? We got 8 thirds minus 3 times 4 is 12, and then 8 times 2 is 16, which, put those together, it's really plus 4. So we really have, what, 8 thirds minus 12 thirds. I'm going to go ahead and evaluate the rest. I don't know if you need to watch me do fractions for 10 days, but I'm going to do fractions for 10 days because it was a no calculator problem. So I'm just going to pause the video, jot the rest of them down here, and then come back. You can too. Okay, not the prettiest thing in the world, but no calculator questions rarely are. For s of 2, I came up with negative 4 thirds. For s of 0, I came up with 0. For S of 4, I came up with 16 thirds. Again, for S of 2, we came up with negative 4 thirds. S of 6, I came up with negative 12. And then S of 4, again, was 16 thirds. So let's see, we have a negative 4 thirds on the outside. Let's see, this would be plus, so that'd be 20 thirds, and then minus 12, whole number, minus 16 thirds. So let's put together all the thirds, and then we'll deal with the 12 if we need to. So let's see, well, negative 4 plus 20 is 16. And then 16 minus 16 is 0. That doesn't sound right. I don't think it's negative 12. Well, dang it. Now I have to pause the video and check my work. Got it. I have found the mistake, everyone. It's right here. I goofed on this. 8 thirds minus 12 plus 16. That would be plus 12 thirds, which would make this 20 thirds. So I'm going to update this one right here, 20 thirds. I got to update. Nope. Shoot. Where's the undo button? There it is. I got to update this one, minus 20 thirds. Okay. So I'm just going to redo this whole line. So I am terribly sorry about that. Let's see. 20 thirds plus, let's see, this would be negative 4 thirds inside the absolute value. So that'll get eaten up, make it positive. Minus 12 minus 16 thirds. So then this will become actually positive. So it's 24 thirds minus 16 of them, which would give us 8 of them. I'm getting rid of that equal sign because I didn't carry the negative 12. And 12 is really 36 thirds. Guys, I have got to stop doing math. I got to follow my notebook more. I've goofed again. Am I just tripping over a negative sign? I know the correct answer is 44 thirds. That's what I have in my notebook. That's what I got on the calculator. If I'm tripping over a negative, but yes, where did this extra negative come from down here? Okay. Positive 12. There we go. Should make that plus 12, plus 12, plus 12. It's all good. See, this is why we don't like no calculator problems. Man, don't like that. Don't like making mistakes, that's for sure. All right. And that was review, right? So 18 minutes in, y'all ready to start the real stuff, the new stuff? Well, I guess this was only halfway review. The concept was review, but the idea of bringing in the pre-calc to solve the integral, that was kind of new. So good news. AP very rarely makes you do something like this. They could, but it's very, very rare, and it has not happened lately. Ooh, maybe that means we're due for one. I don't know. This is typically something we see more like in an actual collegiate course. I know I've seen my fair share of this style problem when I tutor kids going to Johnson County Community College, or I like when my students send me their calculus tests wherever they end up going to school. So wherever you guys go, if you want to send me your calculus tests afterwards, that way I can better prepare the future. You're welcome to send them to me. Yeah. Let's look at one more, and then we'll finish up this video. So this is the big new stuff here. This is where accumulation of change becomes a real thing, and I do not have a physics. It's not a physics problem. It's some other problem where things are changing. So I'll give you a second to read through it here. Okay, so let's just make sure we're kind of starting in the right place. So we have a pair of functions. We have e of t, and this is a rate function. Keyword here is rate of, what was it, of rain entering. And its units are milliliters, but it's a rate. I see the amount is measured in milliliters, and then I see per hour. Oh, per hour, there it is, milliliters per hour, the whole thing. Okay. milliliters per hour. And then, let's see, what else do we have? We have L of T, which is also a rate function. Leaves the bucket according to the variable rate, L of T. And I'm just going to say leaving. I know it says like draining or something. L for leaving, right? And again, that would be in milliliters per hour. So here's the deal. AP loves to do this, and I mean, you know, it would make sense in real life. If you were just measuring something's rate, you could just give it its name. But I want you to think about it like this. Because it's a rate, it is effectively some other function's first derivative. Let's look at the questions. First off, how much rain enters the bucket over this time period? How much enters the bucket over this time period? Well, if I know how quickly the rain is entering, if I want to get to an amount, I just need to integrate that rate, and that will get rid of the fact that it's a rate. It'll get rid of that factor of time. It'll give me with just some measure of milliliters. So unfortunately, I already started with capital E because AP tends to do it that way. But imagine, if you will, an even more capital E. I don't know, something like that, which would be the antiderivative of this guy, right? Effectively, what we know is the antiderivative of this thing at the upper limit minus. Okay, this is ridiculous, Mr. Doohan. Minus the lower limit is that integral, right? And this change would be how much rain entered the bucket. It's not how much rain is in the bucket at the final time, it's how much came in. So whatever, yeah. So let's evaluate that. We can use a calculator here. Oops, I don't know why I erased that. You'll see the function is really weird in both of these. That's because these are typically designed to be calculator problems. And I need to fire mine. All right, so here we go. Integrating from 0 to 7, x squared, cosine of x squared plus 2. And we get out our value. That is an amount in milliliters. So the amount of rain that entered the bucket between times 0 times 7 would be that 14.55 rounded up to 8 milliliters. For part B, it's how much rain leaves the bucket over this time period. It's the same thing. We're going to use an integral to accumulate the amount of something that changed. We know the L function is how quickly the amount of rain is leaving. So integrating it between 0 and 7 should give us the amount that left. And again, this works because I'm integrating a rate. Integrating a rate should get you back to an amount. So let's see. Same thing. We got to punch it in the calculator here. Menu, calculus, nope, not derivative. Menu, calculus, integral. Let's see, it goes from 0 to 7. And this one was 5 times the sine of the square root of t dt. No, I've made a mistake somewhere. Oh, it starts at time 3. God bless. Good news, we can just change up that one little number. There it is. We'll start at 3. There we go. So I got to change that over here too. My bad. See, hey, this is why you got to read the question and pay attention to the context. At time 3, the bucket springs a hole. That's why we have to integrate from 3 to 7. And let's see, our calculator gave us the accumulation of change there. The accumulation of the amount that left was a little over 15 milliliters. So, how much rain is in the bucket at the final time? Well, we would need the initial amount plus the amount that came in minus the amount that left, the amount that leaked or whatever it was. So I'm going to come back to my problem. I do see an initial condition. Don't forget that. It's always like an automatic -1 if you forget that. So 25 plus, we already did the integrals up here, so you could just say plus the 14 point da, 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 minus 15 point da, da, da. If you hadn't done that yet, typically AP doesn't separate it all out. Like part C might be the only question you get here. You could say plus the integral from 0 to 7 of e of t dt, because that's the amount that comes in, minus integral from 3 to 7, this is the amount that leaves, L of t dt. And then you either punch in your calculator or you total up using these numbers, it doesn't matter. You get 24.180. Again, answer in context. It's an amount of water, so I'm saying milliliters. Because this would be a calculator allowed question, this is all the work you need to show. Make sure, again, I've said this a few times over the semesters, make sure you are showing what you plug into the calculator. Even if it's just like this, you don't have to copy that whole function, even if you just reuse the name they had there. You writing this down and then writing this number is good, because what if you miskey it on the calculator? If they see both this and your answer, maybe you miskeyed on the calculator and your answer is wrong, you would still get like the +1 for this. So it's huge. It's very important that you show your work on problems like this. In our next video, I'm just going to be working 2 full AP. Actually, it's 1 full AP problem that involves this. It also goes through some review, some older stuff as well.